Hello, class. So we're going to continue on section 2.7. Right? In the previous video, we saw we were trying to solve this initial value problem, first order initial value problem. We saw that there was no, that this didn't match any of the techniques that we have so far. Like it's not separable, it's not first order linear, right? It is first order, but not linear, and it's not exact. Right? So I said, okay, none of the techniques we have work, so we're probably going to have to use something different, something new. Right? First, before even attempting to approximate a solution, well, if the solution does not exist, then there is no point in trying to approximate it. So we first use theorem 2 from section 2.4 to guarantee that a solution exists to this initial value problem. So we did that work. Right? Now that we know that a solution exists, let's actually go through all the work of trying to approximate it. Okay. So we're going to do it again as I've done recently, just as an example. We're going to work through it, how the algorithm works, and then I'm going to give you the general form of the algorithm. Okay? So approximate y of 2.1 given the setup above. Okay? So since I actually wrote a lot on this slide, let me just rewrite what the setup was. So the differential equation was y prime equals 0.1 times square root of y plus 0.4 x squared, and then the initial condition was y of 2 equals 4. Okay. So we want to approximate y of 2.1. Again, we know that such a solution exists. We don't know exactly where the interval is, right? So by the work that we did in the previous video, we know that there is some interval about x equals 2. Right? So maybe 2 plus, actually, let me draw it like this. Let me just draw the number line. 2 is here. We know that there is some interval here called I naught for which a solution exists and is unique, right? So given that, we're going to try to approximate y of 2.1. Now, if we knew what the solution is on this interval, right? If we knew what y is, we could just plug this in 2.1 into y, right? And then we would get what y of 2.1 is. Since we don't know what y is, how do we approximate y of 2.1? Well, the first step of the algorithm is actually very straightforward. You actually learned this in Calculus 1. What did you learn in Calculus 1? If you have a differentiable function about some input, so I'm going to draw something that's differentiable, so something that's smooth, or something like that. And say we want to approximate our function really close to this input value. So let me draw that in a different color. We want a way to approximate this function, let's label it f of x, for x values really close to this x naught value. What was the method we learned in Calc 1 to do it? Well, you use the tangent line. Why does this work? If you draw the tangent line here, I'm going to draw it in green. Let me try to draw it more accurate. Okay. If you remember, so this is the tangent line. Another word we had for the tangent line was the linearization, right, of a function. So let's call it L of x. So again, L of x here stands for linearization of f. It's the same as the tangent line. Okay. So given this differentiable function around x naught, we know we can find the equation for the tangent line, right, at this point, x naught, y naught. And if you remember, this is a really good approximation for f, for x values really close to x naught. And you can see it in the picture here. It's kind of even hard to distinguish between the function f and the linearization L for x values close to x naught. They seem to overlap, right? You can see, look at this interval here. The function and the linearization are almost the same thing, right? So that's what you're learning in Calc 1. Given a function that's differentiable at an input value x naught, you can approximate the function using the linearization, which is just another name for the tangent line, to the function at that point. Okay. So that's the first step of our algorithm. Well, we can approximate y of 2.1 Notice that y of 2.1 is very close to y of 2. Right? We know exactly what y of 2 is. Right? We know that y of 2 equals 4. And not only that, we also know the derivative at this point, which is the same as the slope of the tangent line. Why? Because we have an expression for the derivative. So we can exactly find the tangent line to the function at this point without even knowing what the function is. Again, we don't know what y is. All we know is that it exists. We can find the tangent line to the function at this point just with the information we have. Okay? So let's do that. So we want to find the tangent line, which again, for the purpose of this section, I'm just going to call linearization. So I'm going to find the tangent line or linearization for our solution, our unknown solution y. So that looks like an x. For our unknown solution y at the point, so the point is x equals 2, y equals 4. And again, this information we're given exact. And I keep mentioning that because when we try to approximate even more values, well, this might not work that well. Now, again, this linearization is only going to work for x values really close to the original x value, which in our case is x equals 2. Now, how close these values have to be to x equals 2 is not something that we can determine with the techniques or the classes we've taken so far. But it is safe to assume for our purposes that 2.1 is close enough to 2.2. So this is going to be an accurate enough linear approximation for the function or the solution. Okay, so let's go through the process. Okay, what do we need for the equation of the tangent line? Well, we need two things. First, we need to find the slope. Again, by definition, the slope is the derivative evaluated at this point. For our purposes, this is the function, right? Remember, for us, this is f of xy. So for us, this is just f of, plug in whenever you see an x, plug in a 2, wherever you see a y, plug in a 4. Right? This is going to be 0.1 times the square root of 4 plus 0.4 times 2 squared. Now, I'm going to put this into my calculator. So square root of 4 is 2. 2 times 0.1 this is 0.2, right? Plus 0.4 times 4, right? And it ends up being 1.8. So again, we don't know what this function is, but we know exactly what the slope is at the point 2, 4. That's the slope. All we need to find the equation of the tangent line is the slope and a point on the line. Well, we know what that point is, right? We know that this tangent line has to go through the point 2, 4 on the function y. So we have the slope, we have the point. Now let's just use the, what was it? The, not, yeah, point slope. Yeah, point slope formula. So what's the point slope formula? It's y minus y naught equals m x minus x naught, where x naught, y naught is the point on the line. And m is the slope. So nothing new yet, right? This is all something you should have seen in Calc 1. It's a typical exercise from Calc 1. So let's find the equation of the line. So what do we have? We have y minus, so the y coordinate is 4, equals the slope we found to be 1.8 times x minus the x coordinate, which is 2. Okay. If we solve for y here, and assuming I did that correctly when I was working this before, I get the line y equals 1.8x plus 0.4. And again, oh, actually, let me call it L of x. Actually, L1 of x, because we're going to be doing this more than once, but L1 of x. And again, what's the picture of this? So our function, which in this case I labeled f, for our purposes is the solution y, a known solution that we know that exists. And here, L of x is our L1 that we found. Again, L1 is not exactly the function f, but really close to x naught, which are, for our purposes is x equals 2. This is a good approximation, which means that we can approximate, y of 2.1 is approximately L1 of 2.1. And again, the explanation is this picture here. For x values really close to 2, our linearization should be an accurate enough approximation of the function. Okay. So what is L of 2.1? Again, I'm just going to plug it into my calculator. 1.8 times 2.1 plus 0.4. We get 4.18. And this is an approximation of y of 2.1. Now, in a lot of algorithms, we want to be able to set up something that's called an iterative method, meaning that we want to iterate through this process a bunch of times. All right, so you find something that works, you want to do that a bunch of times so you can get either a more accurate solution or just something that gives you maybe not something that's necessarily more accurate, but something that helps you approximate things that are further away. That's one other example of why we want to be able to iterate over this process a bunch of times. And that's what we're going to do here. So we know we can use the linearization to approximate for y of 2.1 without knowing what y is. Again, all we knew about y is that it exists and that it goes through the point 2, 4, and its derivative. Okay. Now, let's say we also want to approximate, so approximate now, not y of 2.1, but y of 2.2 using the work above. Now, of course, we could do a linearization again, right? So use the same linearization that we used above and just plug in 2.2. We're going to do something different in hopes of getting something more accurate than that. Because as I mentioned, the further away you get from x naught, right, wherever we're centering our approximation, you can see that if I were to extend this line here, the further away our approximation is from the actual function, right? So we don't want to move too far away from 2. So in terms of the process we made, we don't necessarily want to use the same linearization that we used. Now, what would be the ideal situation? The ideal situation is, so let me write it like this. Ideally, if we knew what y of 2.1 is, so let's say if we knew y of 2.1 equals, let's just call it y naught, we could do the exact same process as we did before, right? We could find a linearization, let's call it L2, for y about the point 2.1 comma y naught. Why? Because we know that this point lies on the graph of y by assumption, and we also know the slope, right? Because it's given to us by the differential equation. This is the ideal situation. Unfortunately, we don't know what y of 2.1 is. However, from the work we did above, we do have an approximation for y of 2.1. So y of 2.1 is not 4.18, but we're hoping that it's a close enough approximation. So what are we going to do? Instead, we will find a linearization for y, not on y of 2.2, because we don't know what that is, right? We're not given, not a 2.1, sorry. We don't know what y of 2.1 is, but on the approximation, but on L of 2.1, which we found is 4.18. Right? So in other words, we're approximating 2.1 comma y of 2.1, whatever that is, with 2.1 and the approximate value we got from the first linearization, which was 4.18. So what are we going to do? Again, same process. We're going to do a linearization instead about the point 2.1, 4.18. Again, this is an approximation of the actual point, right? We don't know that this point lies on the graph, and most likely it doesn't lie on the graph of y. However, we're hoping it is close enough, and we're hoping that doing a linearization about this point is more accurate than doing a linearization about the original point, 2, 4, right, which we already have that linearization. So we're hoping that this is more accurate than just evaluating this linearization at 2.2. Okay? So we are hoping this is more accurate than using L1 of 2.2. And again, the reason why is because the further we move away from the x value 2, the worse this linear approximation, this linearization gets. So we're hoping that doing a new linearization about this approximate point is going to be more accurate. Now I'm going to do the work, and then I'm going to show you a picture of what we did. Okay. So let's find this second linearization, and that's why I'm going to call it. That's why I'm using subscripts. So let's find L2 of x, which again is a linearization about the point 2.1, 4.18. As before, we need two things. So let me do it in red. All right, so we need two things. First, we need to know, to find the equation of the line, right? That's what a linearization is. We need the derivative. So we need to find what dy dx of 2.1, 4.18 is. Well, we know what this is, right? Because we're given what the derivative is on the differential equation. So let's plug it in. This is going to be 0.1 times the square root of 2.1 plus 0.4. Wait, no, this is the y value, right? So it should be 4.18. Did I do the same mistake before? Okay, no, I did it right before. Yeah, so this is the y value, right? So I for some reason I put the x coordinate, right? So 0.1 times 4.18 to the 1/2 plus 0.4 times x squared. So here we put the x coordinate. Right? Again, I'm not going to do this by hand. I'm just going to put it into my calculator. It's 4.18 to the 1/2 power times 0.1 plus 0.4 times 2.1 squared. See what that gives me. Okay. So it gives me something that is an approximation. So this is about, why? Because I think the square root of 4.18 is irrational, right? So it's going to have infinite decimals. So let's just round it up to 2 decimal places. So 1 point, I should just use 3. I think in another section I said to use 3. Let's do it to 3 decimal places. So 1.968. So this is the approximate slope. Okay. We have the slope. Oh, the other thing we need is the point that we know lies on the line, on the tangent line. Well, we have that point, 2.1, 4.18. Now let's just find the equation of the line. Using the same formula as before, y minus the y coordinate, 4.18, equals to slope times x minus the x coordinate. Now here I'm going to simplify a little bit by hand. So this is 1.968x minus 1.968 times 2.1 plus 4.18. Let's see what that is equal to. Again, in my calculator. So negative 1.968 times 2.1 plus 4.18. Okay, so I get 0.0472. So 1.968x plus 0.0472. And again, this is our second linearization. Remember, the goal was to approximate y of 2.2 using a second linearization. So now that we have it, all we do is plug it into that linearization. Okay, so y of 2.2, which we don't know what it is going to be approximately L2 of 2.2, which if we plug it into the calculator is, so 1.968 times 2.2 plus 0.0472. And again, I'm going to round to 3 decimal places. I get 4.377. So let's summarize. We started with some information about our function. Right? First, in the previous video, we checked that the function actually exists, right? There is a solution to this differential equation. Right? So we know that it exists. We know a point on the solution, right? The point 2 comma 4, and we know the derivative on any point. No matter what point we have, what xy coordinate we have, we know the derivative, right? So we use this information first to approximate y of 2.1. Again, we're not given what y of 2.1 is, but we use this picture to explain that we can do a linearization, right? Or find the equation of the tangent line, which is going to serve as a good approximation to y of 2.1. Now, next step was we were trying to approximate y of 2.2. Since the further away you move from x equals 2, the worse this linear approximation that we found is going to be of the original function. Instead of doing that, what we did was say, okay, instead of approximating with this old linearization, what I'm going to do is I'm going to find a new linearization, right, a new tangent line about this point, right? What was the point? Well, we want to get closer to 2.2, so we're going to use the point 2.1, comma 4.18. And again, this is an approximation because this point probably doesn't lie on y, right? Because this is not the y coordinate, this is an approximation to y of 2.1, right? So instead of using the point 2.1, y of 2.1, which we don't know what it is, we use the point 2.1, comma 4.18. And again, the hope is that even though we're doing an approximation here, because we're not using the exact input and output, hopefully it's more accurate than just plug it in the point 2.2 into our old linearization. And again, you can see here that the further away we get from the initial x equals 2, the worse this approximation is going to be. So what do we do? Well, the same process as before. We have a point that we're going to focus our linear approximation about, or our tangent line. We have the derivative, right, given by the differential equation, and we find the second linearization. We use it to approximate y of 2.2. That's the summary. What does this look like as a picture? Now, this is not the actual function y, but I think that drawing it like this gives you a pretty good idea of what we're doing. Right? So I have a function y in red. Right? I have the point 2.2. Right? So the function in green is the first linearization. Right? So what do? We found the equation of the tangent line to y at the point 2, 2. Okay. So once we did that, we wanted to approximate. So we approximated y of 2.1 approximately as L1 of 2.1, right? And that's this point here. Now, we wanted to also approximate y of 2.2. So let me use the same color I used above. We also wanted to approximate y of 2.2. What did we do? We found an equation for a tangent line, not the original one, so not a tangent line that goes to the point 2, 2, but a tangent line that goes through this point, 2.1, 4.18. Again, this point, as you can see, does not lie on y, on the solution, but hopefully it's close enough. Okay? So we found this second linearization, L2 of x, about, that passes through this point and has, the slope that we found using the differential equation, and we use that to approximate y of 2.2. Okay. So you see, each time, and if we were to do this another time, let's say we wanted to approximate y of 2.3, we would do we would find another linearization or another equation of a tangent line that now goes to the point 2.2, 4.83. Right? And again, this point does not lie on the graph of y, but hopefully the error in this coordinate is not that bad, and it's more accurate than just using the initial linearization. And in this picture, you can see that if I were to use the original linearization in green, look how far off I would be. Right? In approximating this point, which was 2.2, 4.38, this linearization in orange has this error here. Right? It's the vertical distance. If I were using the original linearization, instead of finding a new one, my error would be this whole vertical distance here in black. And that's the idea, that using an approximate point gives us a better approximation than just using one linear approximation. Okay? And again, every time we do a linear approximation, we make sure that our line, our tangent line, goes through each subsequent point that we found, right? So our first tangent line went to the first point, 2.2, which was on the graph. Our second tangent line goes to the point 2.1, 4.18, which is not on the graph, but hopefully is close. And then our third linearization, if we were to do it again, would go through this point 2.2, 4.38, which again is not on the original graph, but it's instead on L1. And like that, you would keep doing this a bunch of times. And this is how the iteration is going to work. Every time we're going to use the previous point that we found and use it to find a new tangent line. Okay. So I know this is not easy to understand. So if you have to go through this video a couple times, that's fine. Right? However, this is the general method. Now all we're going to do is find a way to write this method in a way that we don't have to do all this work every time. Right? Imagine having to do this if we want to find 10 different linearizations. It's going to be a lot of work. So instead, we're going to try to find an algorithm that simplifies this work. But the algorithm is going to do exactly what we're doing here. Approximate points using new linearizations each time that go through the previous point that we approximated.